Good morning and welcome to this fifth lecture under adaptive signal processing. So, where we will start looking at adaptive filtering. Essentially, we have motivated now that there are, if you consider statistically the input signal and the desired signal, the Wiener filter is the optimum filter if our objective is to minimize this mean square error, right. So we will see a little more about, having seen the statistical aspect of the signal and the desired signal, what happens when there are variations, or if instead of having a time invariant system, if we have a time varying system, how do we go about handling this, right. So, that is what we start looking at today, and that leads us to this notion of what we refer as adaptive filters or adaptive filtering. So, in the previous discussions, we had seen that for wide-sense stationary input signal and the desired signal and jointly wide-sense stationary signals, we could obtain this optimal filter, which is denoted here as this W. Having known the statistics for Rxx and Rdx, we could obtain this optimal filter. So, then question now is, we are assuming this W to be some fixed value, and that is what we have obtained. But if we, let us say, consider or relax and say, what if D of n and X of n are jointly non-stationary signals, right. So, how do we go about handling this? And similarly, even if we assume stationarity, in practice when you want to obtain this R inverse, there could be, since these are estimates of the autocorrelation matrix, there could be issues in inversions of this autocorrelation matrix, and hence we may not be able to obtain this W exactly as what we desire it to be, right. So, that kind of leads us to this question, rather than just getting one optimal filter directly from this inversion, is there a way of obtaining this weights in some other way, which probably could be an adaptive way or an iterative way for obtaining these weights? An iterative way will just help us get to this W optimal from some W, let us say without any prior condition. If we initialize it to some value, we would have an iterative way of getting to W. We want to look at it in an adaptive way if there is something changing in the system and still we want to update this W, right. So, that is kind of two requirements we have, and that is kind of what we will use as motivation for why we need this adaptive filters, right. To relook at what we had seen before, recall we had our desired signal D hat of n. We could, so note that we are introducing this notion of n now, which we will come back and see why it is, that is assuming it is a time varying signal. So, we would rewrite the same equations, except that now these are all indices depending on n. We have a set of weights which also vary with n. The input of course was also changing earlier, but here also same thing, just for notation sake we have introduced a n as a subscript here. If that is the case, then we have a set of weights which we denote as W here, which again is, if it is a length P filter, we have P coefficients, and the input correspondingly is also length P, right. So, this time index, as I mentioned, has been introduced to indicate that this could be time varying. If it happens to be a wide-sense stationary system with inputs and desired signal, then one would expect this Wn to be the optimal filter at every time instant n, right. So, this obtaining this optimal filter at every time instant n is going to be challenging and difficult, because there are aspects involved in estimating this W, right. So, what if we do not want to estimate this optimal filter at every instant n? Instead, what we want is, we want a way such that if we get or update this W, rather than getting to the minimal at one step, we look at ways of updating W so that this error keeps decreasing, right. This mean square error, for example, keeps decreasing. So, if that is what we would like to have, then it is possible that we can look at this problem as, rather than just getting to get one W directly, we could look at an iterative way of trying to get to W at n plus 1 instant, starting from a W at n by appropriately perturbing or updating this W. Okay. So, how do we do that? Why do we do that? Is what we will discuss in the next few slides, as we try to kind of define what we wanted to do, right. So, what is this motivation for adaptation or filtration or iteration? One main thing, one possible thing, if you assume that White-Sense stationarity is still available, the difficulty with Wiener filter was that if we have, let us say, a very large filter, which means a large order, the computational complexity can be demanding, and so it is going to be difficult to achieve. Similarly, because of this larger matrices, at times when you are trying to estimate this autocorrelation matrix, remember or recall, this RXS is an actually estimate. So, this estimate is usually, as we discussed in the random process, it is an estimate from a given realization, and if we are going to estimate RXS from a given realization, this is going to depend on the number of samples we use to estimate RXX, right. So, this quality of estimate and how do we invert it, all of these play a part in trying to get this optimal solution. So, this is again another difficulty with just using this Wiener filter directly, right. And indirectly or implicitly, we know that to obtain this solution we need to always estimate or have an estimate for RXX and RDX, which again can be time consuming, because as I just mentioned, it takes certain number of samples, let us say n samples, to make any of these estimates RXS, RDX. So, these kind of prevent, even for the typical Wiener filtering solution, rather than just trying to get the W directly, if we can have an iterative way, that may be more useful, right. Of course, if this is not a White-Sense stationary signal, then what we want is this notion of adaptation also, right. It is not anymore just iteration, but iteration and adaptation to match the signal which we want. So, this is a way of looking at a slightly different way, as we had seen in the Wiener filtering case. So, this X of n is something similar to what we had, which could be a D of n corrupted version, and that is X of n, that is input to the system which we are interested in designing. It is going to give an estimate of the desired signal. Again, depending on the problem, we may or may not have access directly to this D of n. Irrespective of it, if you look at the difference between the estimate and the original signal, you get an error signal. So, we need an adaptive algorithm or an adaptation which takes the error as the input and also possibly the input observed signal, and with this we are going to update or perturb the weight by a factor, let us say delta Wn, right. So, if we can update this Wn at every instant of time in some way, so at every instant it may not minimize the mean square error directly, but this adaptation will make sure that with time this error will go down, right. So, if we look at what is that we need in this adaptation should ensure that when we look at this error should be decreasing. Again, we are again re-looking or just considering the mean square error. One could change this problem to not look at mean square error and some other error, but depending on the error function, there are things which can be done easily, and sometimes it may be difficult to do few things. This mean square error has some nice properties which also helps us in adaptation. Irrespective of it, we have to make sure this adaptation, with this adaptation, this error decreases with every iteration, right. If the signal happens to be a stationary signal and system is still time varying, then we should be able to say that with adaptation and with n going to n infinity, we should reach this optimal filter, which from we recall, what we can recall is Rn versus Rd, right. This is just a simple cross check to make sure that the adaptation works well, right. As much possible that we should not be depending on estimation of statistics, because that is one of the motivation why we want to move away from just using the Wiener filter. So, we will try to still see whether such a thing is possible. If not possible completely, at least partially can we eliminate use of this estimation or use of the statistics of the signal, and how do we handle this, right. in addition to all these things, what is more important, and that's where kind of the probably effectiveness of the algorithm is, if in case the signal is non-stationary, right. So then any change in the signal has to be monitored and the system has to be adapted. So that notion is referred to as tracking. That is, once you have a system which, let's say, does well and minimizes the error, if something changes suddenly in the input, the signal the system should again be able to track this change and update this weight, right. There may be a lag or delay between the settled weight and the new set of weights, but it's desirable that this algorithm can track such changes, right. So in this discussion, we may, when we look at some adaptive filters, we may not talk too much about this tracking is itself, because once we have an algorithm which can adapt and settle to an error, tracking is not that difficult, right. So we will not spend too much time on tracking, but we will look at how is this adaptation happening, right. So with that kind of idea about why we need adaptation and what should such an adaptation algorithm do, what we will do is we will just look at one way of doing this adaptation. This may not be the practical way of doing it, but that sets a sufficient background to actually look at a more practical algorithm which will use for this adaptation. And that essentially is from something which is well known from our math background. When we are looking at functions and we want to find the value which minimizes this function, we have several algorithms. One class of algorithms are these gradient descent algorithms, and in that specifically what we will look at and we will use is called as the steepest descent algorithm, right. So let's say this is, let's say, just to be convenient, let's say this is, let's say, the error function, the error or function which we are interested in. In this case, it's let's say a function of two variables. Let's say in this case, just to be consistent, let's say these are two weights which are W0 and W1, and if we do plot this zeta n, right, see zeta, right, this is the function which we are interested in. If we can find, in a theoretical case, if we find an expression for zeta and we plug in this value for W0 and W1, and let's say these are these different choices of pairs of W0 W1, okay, this is one pair, this is one pair, and we keep changing this, and that's what we have here as the different values for zeta, right. So with this looking, so think of this as a it's a 2D plot with 3D, if you want to think of it as it has an z axis, let's say, coming out from the paper. So it's like a paraboloid, and you can see that this paraboloid has the minimum at this point, which is the center, right. So if we really want to, let's say, look at it in the Wiener filtering case, our ideal optimal point would be this point, right. The filter coefficients would be corresponding to this point here, right. That's what W optimal would be. W optimal would be W0 optimal at this point and W1 optimal at point. So now, rather than applying this directly on the having statistics for Rx and Rdx, what steepest descent tries to do, as we would already know, you start from some point, let's say that is, let's say this point here, right? That's this point. So you move in a direction. So the gradient, if you look at the paraboloid, is going up. So you move in the negative gradient. So you move some like this. Then the next point, and then the next step is move again like this. Then again at a direction perpendicular, you move like this, again like this, and move like this. Right. So this is our steepest descent. Right. This, let's say, indicates the trajectory for the steepest descent, right. So this is the starting point, and we are hoping that by moving in a certain direction in with certain step size, we would attain this minimum point, right. So that is essentially what we want to do. That is, rather than just getting to this point directly, can we search for the minima, that is a point which minimizes this function in an iterative way by moving in a direction that minimizes the function, or in a direction that is the negative of the gradient, okay. So instead of going up, if you go up the gradient, you will go to the maximum point. If you go down the gradient, you will go along to the minimum point, right. So if we can do that, then the objective is that you will have this, it will be of this form. You start with some wn plus 1, let us say in this case these are vectors, and you have a starting point, it should be w0, you update it by some factor, and then you get to the updated weight, right. So what is this factor delta wn? We want to look at it as a gradient of this error function, not just the gradient, it is the negative gradient times some scale factor, right. So this in the gradient design literature is usually referred to as step size, right. So of course one need to be careful about what step size to use. For a standard gradient design algorithm, there are algorithms to line search algorithms to obtain the step size, but for us we need just some bounds on this, so that when we obtain a weight, this behaves in a meaningful way, right. So this is going to be the approach, that is we would look at a more practical application later, or a practical approach later, and for now we will just say what does this mean when you want to do this update in weight. Does this weight has certain properties which we had required it to have, and whether such an algorithm just itself can be used to update our weight, right. It turns out it can be done, and so that is why we will refer to this as a while for discussion we will refer to this as the steepest descent adaptive filter, right. So this filter should be able to handle a case where even if it is non-stationary. So nothing changes here except the desired signal. Now we have introduced this notion of n, as we had mentioned before. So this desired signal is again the inner product of the input signal times the weight vector. Initially we will start with some 0 w0, which we do not know what it is, and eventually what we want is we want to look at this error function zeta n at different times, right, or different steps with iteration, what happens to the zeta n, right. So for that we need to look at this gradient of this function, which is let us say with respect to this weight vector. Again we will look at wn star, that is the conjugate or complex conjugate of the wn, so that it is more generic. And if in case that this is inputs happens to be stationary, then we should lead this wn should lead to be this rxx inverse times r dxn, assuming you can estimate these rxsn inverse, right. But that is only in the ideal case where we have access to these things directly. But if not, what do we need? We need to update the weights, this is wn, using this error function zeta n. What do you mean by using this error function zeta n? Which means we should be able to find the gradient. So hence this is why when I said we are using this mean square error, which has certain nice properties. One of the properties of this function is it is differentiable at all points, and we could obtain the minima. Depending on the zeta n, there could be multiple minimas, but for the scenarios which we look at, there will be usually one minima, and that we should be able to obtain, right. So now let us just look at, of course there is nothing new here, we just have to look at what is the gradient of the function. This is something we had seen many times before, but just let us re-look at again, just so that it fits into this current setup, right. So we have our weight wn plus 1, it is going to be an update on this wn, it is going to be updated based on the negative of this gradient, and then we just to be consistent we say that this step size is mu, okay. So this mu is an important aspect of this problem, and we need to somehow find it, right. Otherwise it is just the gradient of zeta n with respect to the weight, and if you look at what is this gradient of the weight zeta n with respect to weight, zeta n is this difference between the desired signal and the expected signal, which is d hat of n here. and the difference squared is what we want, but then we are looking at mean square error, so we have an expectation here, right. So this is again something which makes it different from the standard gradient descent, because there is some kind of randomness or stochasticness to this. So this actually, these class of algorithms can be looked at as stochastic gradient descent. So hence this is for those of you who are familiar or know a little bit about machine learning. So this is that stochastic gradient descent, right. So you see that there is some connection to this, and how this behaves is all very critical for many algorithms. So we will try to just motivate what choices could be used to get this mu, right. But the only thing I wanted to point here is there is an expectation here which brings in the stochastic nature of this problem, which means we are still fine in terms of random processes being input to the system, right. It could still be time varying system. So this expectation is this written here. We could apply the expectation, again do this dn minus wn times dn minus wn xn conjugate. You expand it out. The first term will be just depending on this d of n. The second term or the last term will be a inner product of this term wn transpose times expected value of xn times xn transpose times wn, that is this term, and this last one is this cross term here, right. So this is again as a good exercise just to re-look at how you get this. Next we look at the gradient. Again recall this gradient is a vector, this w is a vector. So we are trying to look at a gradient of this scalar here with respect to the vector, which will again be a vector, right. So this RDD0 is independent of this w, so this does not come into the picture here. So this term I guess you should be a bit familiar with, or you should get familiar with, is looking at gradients of gradient of the scalar with respect to vector, right. So if you use that, the notation here and this properties here, this is something of like your a squared b, where just read matrices you can't write a squared b, so it's slightly different. So this will turn out to be this term, right. So do verify that you could go from here to here applying some properties of this gradient of scalar with respect to vector. Here it's kind of straightforward, it's just a function of wn, and so you have this 2 rdx, right. So ideally we have this gradient term to be just this 2 rdx. So this just 2 is a scaling factor which we would later drop, but for now I am just leaving it here. So using this gradient in this weight update wn, what we have for wn plus 1 is what is shown here, right. So this wn plus 1 is now wn minus mu, which is the step size, times our gradient, which is what we obtained in the previous slide. So this 2, as I said, is the scaling factor we could drop here just for convenience and to be consistent with the literature, meaning this mu can be thought of as 2 times mu dash or something like that. So let us say maybe we will just do that, let's say let's make this mu dash 2 mu dash is mu, okay. So just to be consistent that this is only mu, right, and then this negative sign gets here. So we have a form of wn plus mu times this, right. So what this shows is it is still not something which we could just do because we need to know the statistics again. This is just convincing, or this is just showing us if we go about doing it in a steepest descent way, here is how we would update our wn, right. What we could use this is for is, if at all this happens to be a Whiteson stationary process, we know that this term should go to 0 because that is how the optimal weights we obtained were. So if it does go to 0, you can see this wn plus 1 going to wn, right. So that kind of convinces that even if you use a steepest descent approach for a stationary signal, it will turn out that it could obtain the optimal weight, and that w optimal n plus 1 will be the w optimal, right. So that is what is said here, that for stationary or Whiteson stationary process we could show that this goes to 0, right. So the more interesting case is when this is not stationary, right. So then that means this may not be easily evaluated. So, we need some way of trying to do this estimate or approximate this estimate with something else, right. So, what is that is something we will look at next, but for now we need to just realize that given this setup here, which is like the steepest descent, or if you want to think of a stochastic gradient descent, this is the way we want to iterate or update this weight or adapt this weight, so that we minimize the mean square error at every time step, right. So, we will see later that there is some specific requirement on mu for this convergence to happen, right. This convergence has to happen in any case, whether it is stationary or non-stationary, right. What is that condition on mu is something important. We will try to motivate that by saying on looking at what is the weight update and how is the weight update happening, right. And as I mentioned, this still depends on the statistics which we would like to eliminate, right, which we would want to which we do not want, right. So, this is something we need to look at. Hence, we will see in the next lecture how that this steepest descent like approach or stochastic gradient like approach has given us a way to update or iterate or adapt these weights, leading to an adaptive filter, but there are still some things hidden here which we would like to eliminate, right. So, just think about this, the statistical nature of this equation comes from an expectation, right. So, we will have to see how do we kind of handle or eliminate this expectation from this equation here, and if we can do that, then we would have a practical way of doing this steepest descent and then obtaining this optimal weight. So, that kind of ends this discussion on steepest descent for adaptive filtering. In the next lecture, we will look at more practical application, which will be the least mean square or LMS filter, which is one of the main adaptive filter algorithms. Thank you, and we will see you in the next lecture.